Hi guys, in this video we are going to explain the code we wrote in first.s. The first line, .code 16, is a directive which instructs the GNU assembler to generate the object file in 16-bit mode. As by default, GES generates 32 bits or 64 bits code depending on the configuration. The reason why we need 16-bit code is that at the time when this program runs, the CPU is in 16-bit mode. All directives have names that begin with a dot or period in GES. These directives are not translated into any machine code, but only tell GES how to organize or translate the code into machine code. The second line code .glob is a directive as well. The function of this directive is to make the symbol, which is _start in this program, visible to the linker. Program first.s only has one source file, while for programs which have more than one source file, the .global directive will make the symbol can be seen by other object files at a linking stage. We go back to the third line of the program. _start indicates the default program entry point. Linker later makes the executable file start from the first instruction, which is just after the symbol _start. In other words, the linker at the linking stage will search all object files for a symbol named _start, then set the entry point of the program. In line 4, move $26, percentage mark CX, where move is opcode. $26 and percentage CX are its two operands. A opcode or operation code can have 0, 1 or more operands. 26 with a prefix $sign indicates an immediate number 26 in decimal. A register name CX with prefix percentage sign indicates the content inside of the register. This instruction tells CPU to move the immediate decimal number 26 into the register percentage CX, which is a 16-bit register. The whole line is called an instruction statement. Did I say a register? So what is a register? A processor register is a quickly accessible location available to a computer's CPU. Registers usually consist of a small amount of fast storage. How small is it? For the 8086 architecture, the size for each of the 8 general-purpose registers is 16-bit, or 2 bytes. Let us quickly go through what are these 8 general-purpose registers. The first one, originally used in arithmetic operations. Second one, CX, used in shift or rotate instructions and loops. The third one, DX, used in arithmetic operations and input-output operations. BX, used as a pointer to data. Then, the stack pointer register SP points to the top of the stack. We will cover the concept of stack shortly in this course. and then the stack base pointer register BP used to point to the base of stack. The source index register used as a pointer to a source, and the destination index register used as a pointer to a destination. By now, we only need to know there are 8 general-purpose registers for 8086. The more we use, we will get a better understanding on these registers. Similarly, line 5 move $0x 0903, %dx moves the data which is a hexadecimal number 0903 to register dx. Line 6 move $0x 000C, %bx moves the hexadecimal number 000C to register bx. Now we look at line 11, MSG :ASCII, my first computer program, in quotes. The ASCII, which starts with a dot, means it is a directive. It tells the assembler to reserve space for string or text, which is the following: my first computer program for this program. The MSG before the colon is called a label. With this label, we can refer to the address of the string MSG. So, what is ASCII? ASCII, abbreviated from American Standard Code for Information Interchange, is a character encoding standard for electronic communication. Most modern character encoding schemes are based on ASCII, although they support many additional characters. Let us see what does Wikipedia say regarding the ASCII. Great! We now have a look at what does Wikipedia say regarding the ASCII code. We input ASCII wiki and press enter. We click into the first one, and you can quickly browse the introduction of ASCII. It's a long introduction. We quickly drag this into the middle, and we focus on two things. The first one, you see, it says the control characters. Actually, all the ASCII code is divided into two groups. The other group is the printable characters. So, which means these control characters are not printable. We have a look at what are they. You can see in this decimal column, there are numbers from 0 to 31, and plus the last one, 127. That's 33 in total, the control characters. We see the first column, there is a binary format of the numbers. We can see there are 7 bits. So what's the number of the zeros and ones in combination? If you are given 7 bits, the answer is 128. As third power of 2 is 8, is it? So the sixth power of 2, that's 8 times 8, that's 64. And then we times 2 again to get the seventh power of 2, that's 128. So if you are given 8 slots or 8 boxes, each box you can only put either 0 or 1. So you can have as many as 128 different combinations of these zeros and ones. As we understand, in a lower level, the computer can only use 0 and 1 to represent the information. So we can also say these characters are just a kind of explanation of these numbers, of these 128 numbers. Then we quickly move to the printable characters. You can see from the decimal number 33 to the very bottom, the 126. All of these are the printable characters. And on the right, you can see what are they. So the first one is space, and then a couple of signs, marks, and then 48 in decimal. That's actually for character 0. Then for the uppercase letters, and lastly for the lowercase letters. You can review more if you want to learn more about the ASCII. Now we come back to see line 7. Move $MSG, %BP. This moves the address for the string of my first computer program to register %BP. Line 8. Similar to line 6, move $0x1301, %AX. Moves number 0x1301 to register %AX. The INT opcode here is an interrupter, which forces the CPU stop executing current task and start calling a routine, or can be called a handler. Even we can think it's a function. This routine is just another piece of code stored somewhere else. We can imagine it is in somewhere of the BIOS. In this case, the address $0x10, which is decimal number 16, is given to the CPU. Then CPU searches a table called interrupt vector table, or IVT, to find the location of the handler and then execute the code inside of the handler. Once the interrupt handler finishes, the CPU comes back to execute the next instruction, which it leaves before the interrupt. The concept of interrupt is not hard to understand, isn't it? Actually, this kind of interrupt is usually called software interrupt. We will talk on other kinds of interrupts shortly in this course. The only confusion for us now would be how does the interrupt instruction work for our program? Let us go search the answer. Right, we have a look at the IVT, the interrupt vector table. So when we tell the BIOS which function we are going to invoke, say in our case the int $0x10, then the BIOS starting check this table, and we click into this 10. You see all of these are in hex. Click into 10, and then we see there is a long list, so we need the other parameters to locate which subroutine we need to invoke. You can see there's AX, so we quickly search. In our case, our AH, which is the higher button of the AX, of the register AX, is 13, so we quickly search 13. And then we click into the first one, as the explanation of the first one is write string. I suppose that's the right one. We click into it, and then we see there is a explanation on how it works. So the first line H equals to 13H. H means hex, which means 13 is a hex number. In our case, our AX equals to 1301. And the second line, the H, equals write mode. And in our case, the AL is the lower byte of the register X, 01. So which means the first bit of 0, 1 is 1, is it? So we only need to see the first line byte 0 as the byte 0 is set to 1 in our program. It means to update the cursor after writing. So we can see the cursor is still flashing when the program has finished printing the string. And then we see the next line. The BH is for page number. In our case, the BH equals to 0, which means the first page of the screen. Actually, we can guess BIOS takes the screen or our monitor as a model of many pages of a book or something. Then the second line, the BL, that's the attribute if a string contains only characters. In our program, yes, I mean the string my first assembly programs are all ASCII characters. And then the CX, that's the number of the character in string. In our program, the CX, the number in it is 26, which means we are going to print 26 characters. If you count my first assembly program, that's 26. And then DH, DL, that's the row and the column at which to start writing. So by now we can guess with these parameters, the BIOS knows how many characters we are going to print and where are they. The DH in our program equals to 09. You can see on the left side of your monitor. And 0x is for the column, so the BIOS will print the string onto the 9th row and the 3rd column. So you can check that shortly. And the last one, the ESBP, that's a combination. We won't disclose the ES too much here, but for now we can understand that the combination of ESBP is the address of the string. We can see the BP in our code. We assign the address of the MSG, which is a string, to BP, so the BIOS can know where our string is. So basically the whole BIOS, this interrupt program, we can understand in this way. We give them the size of the characters, the location of the string, and where to print them, and the attributes. We will talk about the attributes later. And then the BIOS will know where to find this string and where to print them. So lastly, when the BIOS finish this printing, it executes from the subroutine, which is this interrupt, and then the BIOS returns back and gives the time back to our program, which is for the next instruction, the JMP loop. That's very easy to understand the interrupt, is it? Go to this Wikipedia page, the BIOS color attributes, to see how the color attributes is defined. We can see there is a list of BIOS color attributes, and in our program we use 0C for the lower byte, and you can see actually BIOS use 4 bits, which is half byte, to represent 16 different of color. You can see the first line, that's from 0 to number 15, that's 16 different of colors. We remember originally in our program we use 0C, which is light red. So you can see that's hex number C. Actually, we can change it to any of these from number 0, like 00, 01, until 0F. And you can try it on your computer, change the source code of the first DOS and then reassemble it and relink it and run it to see whether it works. Line 10, loop, colon JMP loop. Let CPU jumps to the label loop, which again let the CPU jumps to the same instruction. So it's a data cycle which will freeze the monitor. When we run the program, the CPU would keep doing this instruction until we close the emulator. The last two lines are all directives. .org 510 tells the assembler to put the next instruction or data from the 510th byte of the whole executable file. As by now, the machine code is far less than 500 bytes, so this will let the assembler to fill a number of zeros in between the end of MSG string in our program and the location of the 510th byte. The last line, .word 0x8855, will fill a word which is 2 bytes at the 510th and 511 byte location of the line. Actually, these two numbers are magic numbers. Remember we mentioned that after the post or power on self-test stage, the BIOS would be searching for a bootable device. When the BIOS program starts searching any bootable disk, it examines the first 512 bytes of the disk. If it finishes with 0x8855, it thinks it's a bootable disk, and then BIOS program copies these 512 bytes into the memory. Then the CPU starts executing the program from the memory address 0x7C00. By now, we have covered each line of our program. That's all of this video. See you in the next video. Hey guys, in last videos, we have translated our first source file in assembly language, the first.s to first.o using the GNU assembler. Then we translated this object file to a runnable using the GNU linker. And after that, we downloaded a Bosch's package and modify the bootable device. And then we see our program was running and the message was displayed on the monitor. In this video, we are going to see if we make some change to the first.s. We have already learned that on the 6th line, this 0C will determine the color of the letters that are showing on the monitor. If we change this 0C to 0D to see what happens. Now we need to use the GES assembler to translate this source file to object file and then link it, and finally we can run it. If we want to combine these 3 steps into one step, that would be much easier, is it? We will try it now. All we need to do is firstly create a text file, and then we open this text file. We put first commands s.s. How to make a script file with bash commands on Linux. This page says we have to put a header, number sign, exclamation mark, space, /bin/bash in the first line before the 3-line commands to let the bash know this is a script file. Let's close it to try it. Before we do that, we also need to change the permissions. Right click and go to the permission table, and then check this allow executing file as program, and then close it. Then we open a terminal to see whether we can run this. Run not found. I suppose we need use a // then we can see it is running. So we don't need to key in the 3 line of commands, we just need to key in // and run to see whether the changes has taken place after every time we change the source file. Press enter to see, yes, I think it is working. The color of my first assembly program has changed to magenta. That's all of this video.